You ever stop and wonder how a modern computer chip with literally billions of components actually manages to work without failing all the time? Well, it turns out there's this hidden world of secret passages and internal checkup systems built right into its design. In this explainer, we're going to dive into this amazing world, a concept known as design for testability.
So, to really get our heads around this, let me ask you a question. Imagine your job is to inspect a city that has 1 billion separate rooms. You have to check every single light switch, every window, every lock, and make sure it all works perfectly. How in the world would you even start? Well, that is the exact scale of the challenge engineers face with every single microchip they make.
So, to understand the solution, we first have to appreciate the just mind-boggling scale of the problem. We're talking about a city on the head of a pin.
Now, this analogy between a skyscraper and a microchip, it works perfectly. A modern chip has billions of transistors. Think of those as the individual rooms. It has miles and miles of microscopic wires, which are basically the corridors. But here's the critical part. Just like one bad beam can compromise an entire building, one single faulty gate out of billions can cause the entire system to fail. Your phone, your computer, your car, boom. It could all crash because of one tiny microscopic error.
And here's the real kicker. At this scale, trying to be perfect is physically impossible. These tiny, invisible manufacturing defects, they're just gonna happen. It's inevitable. A stray particle of dust, a tiny variation in a chemical process, any number of things can create a fault. So if you can't build them perfectly, how on earth do you ship billions of them that work perfectly?
Well, the answer is just so clever. Instead of chasing impossible perfection in manufacturing, engineers build secret passages and trapdoors right into the design of the chip itself.
This whole way of thinking is called design for testability, or DFT, and it's a total shift in mindset. The idea is you embed these special features directly into the circuits. It's not an afterthought. It's a core part of the design from day one, with a single goal: make it super easy to test for faults after the chip has already been made.
DFT really boils down to two key principles: controllability and observability. Let's go back to our skyscraper for a second. Controllability is the power to set any state inside that chip. It's like having a master key that can unlock any door and flip any switch in any one of those billion rooms. Then you have observability. That's the power to see any result. It's like being able to place a tiny camera in any room to see if the light actually turned on when you flip that switch. You have to have both, otherwise you're just flying blind.
So, how do engineers actually build in this kind of, godlike control and observation? Well, they've got a powerful toolkit of techniques they weave right into the chip's blueprint.
This toolkit has all sorts of clever strategies, like scan chains, built-in self-test, boundary scans, and a few others. For this explainer, we're going to focus on two of the real workhorses, the foundational techniques of the DFT world: scan chains and BIST.
Okay, first up, scan chains. This is such a great illustration of that secret passage idea. What engineers do is they link all the key components, these things called flip-flops, together into one long chain. It's like a conga line. This lets them send a test signal in one end, have it snake its way through every important part of the circuit, and then they just read the result that comes out the other end. It's a direct, remote-controlled inspection route right through the heart of the chip. Brilliant.
All right, the next technique is even cooler if you ask me. It's BIST, which stands for built-in self-test. This is like giving the chip the ability to perform its own medical checkup. They add special circuits that can generate their own test patterns and then analyze the results right there, internally. The chip literally tests itself and then reports back if it's healthy or not. And this is huge because it dramatically reduces the need for all this expensive external testing equipment.
Now, building all of this extra circuitry into a chip isn't a small thing. So why do companies invest so much time and money into it? Well, the payoff is, to put it mildly, absolutely massive.
The benefits are just crystal clear. DFT is what ensures the chips in our cars, in our medical devices, are reliable. It drastically cuts the time and cost of testing. It lets engineers find a super high percentage of potential faults, which, by the way, is what makes it even possible to test these massive chips in the first place. And all of this helps companies get better products out the door faster.
So, the crucial point is this: DFT completely changes the game. It transforms testing from a bottleneck into a streamlined, integral part of the design cycle. It's no longer this slow, painful step you do at the very end. No, it's a smart, efficient process that's woven into the very fabric of creation itself.
But, there's no such thing as a free lunch. This incredible power to test everything comes with a few trade-offs that engineers have to make.
First, adding all these extra test circuits, well, it takes up space. Engineers call this area overhead. It makes the chip physically a little bit bigger. Second, all that extra logic can add tiny delays which can potentially impact the chip's maximum speed. And finally, planning out this complex test architecture, it just adds another big, challenging layer to the whole design process. But those challenges, they are a calculated cost. At the end of the day, design for testability is an absolute cornerstone of modern electronics. It's this sophisticated balancing act between the cost of that extra circuitry and the completely non-negotiable critical need for reliability in all the devices that run our world.
So next time you use any piece of modern tech, remember that hidden city inside it and the brilliant architecture of secret passages that make sure it all just works. And, it leaves us with one final thought. As these chips get smaller, more complex, and woven into every single aspect of our lives, what's the next frontier for making sure they're perfect?